All the presenters, everyone that attends this conference is so friendly, so willing to teach, so willing to learn from you too. So it's not just watching these videos, it's kind of getting that insight afterwards and around at dinner, at drinks, like all the other aspects of the conference besides just like that technical information.
All right, let's start going. Thank you for coming to my talk. Not really sure why you chose it, but I'm glad that you're here. My name is Nina Rands, the obligatory introduction. I'm a cat owner, coffee drinker, chocolate lover. I seem to have a thing for the letter C. I don't really know why. But more importantly, I'm a committee member. I have been one for 10 years now. I sit in the core group, obviously, which manages the first 16 chapters of the standard and focuses mainly on the syntax of the language. My first addition to the standard was actually a comma. And I am forever known as the comma supervisor of the C++ standard. I have also recently been appointed as the subgroup chair for the C++ liaison group. There's definitely a pattern, so why not talk about CTAD? On a more serious note, why am I talking about CTAD? So recently I helped a very, very smart group of people write a book. We've finished it, it's out now, go get it, it's awesome. And the book talks about the modern features of C++, mostly C++ 11 and C++ 14, because we just couldn't put anything more in the book. We talk about what features you get and how to use them safely and what pitfalls to be aware of. Now it's 11 and 14, the next step is obviously 17, and as a part of my research for that next step, watch this space, I've done a deep dive into CTAD, and I thought, well, why not give a talk about it? So here we are. What's in this talk? We're going to talk about what class template deduction is, and from now I'm going to call it CTAD because class template argument deduction is a mouthful, and how you can use it to make your life easier. We're going to cover the principles of how it works and things to be aware of when it comes to CTAD. CTAD is one of those features that isn't always very popular with people, but I think if you know what you're doing, and I think if you're familiar with it and understand what's happening, it's really a very, very nice feature. What we will not be doing today is going into in-depth explanation of CTAD rules. I know some people might expect this because I'm a core member, but that's not what we're going to do today. The reason for that is that would just take much longer than an hour. The original rules that we had in C++ 17 for CTAD were fairly simple. But the things that got added in C++ 20 is kind of made the whole thing explode. So yeah, probably a lecture in itself. The other thing we won't be doing is an extensive tutorial on how to write your own deduction guides. Again, this is probably a lecture in itself, and it's more about library design than it is about core feature, which isn't my forte, to be honest. I'm also not going to be bashing CTAD. I'm sorry to disappoint. It was kind of funny because when I submitted this talk, somebody said, oh, not another talk that's going to bash C++, because they immediately assumed that I'm not going to like it. And to be honest, I had no opinion on CTAD when I started writing this talk. I wanted to make it an objective talk that presents both the good sides and the bad sides, so you can make an informed decision on what you think about it. I actually came to like it. I think it's quite useful, and I'm glad that we have it. I'm also not going to be doing a CTAD sales pitch, which is kind of funny to say after what I've just stated, that I like it. But I am going to try and be objective. I am going to present the possible issues you might have with CTAD too. This is a bring your own popcorn talk. So, what is CTAD? We can't really talk about CTAD without talking about the template argument deduction that happens for the function templates. So here it is. We have a function template. It takes one template argument. Let's see if my thing works. Ooh, there we go. We take one template argument, and then when we try and invoke it, we can specify the template arguments explicitly, and we will definitely get a myfunc int specialization. We don't have to do that. We can omit the explicit template parameter and just let the compiler deduce what we want, and then the compiler will go away, it will look at its own rules for template deduction, and it will deduce int, and again invoke myfuncInt specialization. This is called template argument deduction. We've had it since forever. Unfortunately, before C++17, it only worked for functions. It didn't work for classes. So if you wrote a template class and you had constructors that were very similar to the signature of that function earlier on, you still had to explicitly specify the template arguments. There was no other way to create an object. So people, clever people, thought, well, I'll just reuse the function template arguments, and that's how we got make functions. Oops, skipped one. So instead of having the template arguments being deduced from the class, we used to use function template argument rules to get deduction in these make functions that we would write for our class templates. That ended up in a lot of boilerplate code. And not only that, before C++17, it could introduce additional copies, and it didn't really work all that well with move-only types. So people said, well, why not have compiler help us here in the same way that we're doing already? Instead of us making this make functions, let's have the compiler do the same thing. So that got accepted. And then in C++17, we could write this. We could omit the template parameters of a class, and the compiler would deduce it for us. This is class template argument deduction. It has its own special name, class template argument deduction, as opposed to just template argument deduction, because it's slightly different to template argument deduction. And we're going to see why. So what does it do? I used to have to write a vector of ints like this. I had to specify the integer template argument. But with CTAD, I don't have to. Now, this is not a very strong case, but it's a kind of a key code. And to be fair, this is what I do all the time now, because it does the right thing, and it saves me thinking about the template arguments. It doesn't work just with one template argument. It works with many. They don't have to be of type template arguments. They can also be non-type template arguments. So here we have an array that takes the type store and the size. I used to have to specify both, but now I don't have to. Everything gets done for me. Yay. Here's a line where my template arguments are actually taking up majority of my declaration. And last year, Marshall Clow gave a very good talk also on CTAD, and he had this slide full of letters. And then by the end of the talk, using auto-deduction and CTAD, he reduced it to these 3 tiny lines. And you could see what was going on, and you could also see the bugs in it. So CTAD doesn't just make our life easier by writing code, it also makes code more readable. And then we come to iterators. I really don't like iterators. I don't like thinking about iterators. Sometimes it's a constant iterator, sometimes it's a reverse iterator. I just don't care. I use auto whenever I can use auto, so I don't have to write it out, and then the compiler just deduces the right iterator for me. Except if I want to put it in a class template or in a container, then I have to call it out. Now, don't do that. This is not a very good code. This is just demo. With CTAD, I don't have to think about that anymore. Now, good thing about CppCon is you go to these lectures and you learn new things, and then you get to connect things between different features of C++. And I was at the great talk on Monday by Jeff Garland about ranges and things that you get in ranges. And he had an example on the, on the screen that I thought is a perfect example for my talk. And the reason it's a perfect example is because it shows when you should use CTAD and when you shouldn't use CTAD. So here we have a vector of string. We fill it with some words. Thank you, Jeff, because he provided the example. And then we create a join view over that vector of string. Now you'll notice that in the first line, I don't use CTAD. I explicitly call out string. This is because even with function templates, whenever you wanted to create a string, you couldn't just let the compiler deduce it from the string, the quoted string, because that would end up as a const char star. You had to explicitly say, I want a string. So in this case, we don't use CTAD. In the second line, we do. Here's the second line without the CTAD. Now, if you want to learn a new thing, like ranges, it's already a new thing to think about. You have to start thinking in ranges and views. Now, if you also had to think about the template arguments that you had to give to your views, the entry point all of a sudden becomes much more difficult to get to, because not only do you have to learn about how views and ranges should be used, you also have to learn all these funny template arguments that you have to give to your classes. And that's just raises the barrier for entry, doesn't it? So this is a great usage of CTAD. You simply don't have to think about the fact that your view isn't actually a view of vector of strings. It's a view of a ref view of vector of strings. One win for CTAD. I swear I'm not selling CTAD. I just like it. I think it's a nice feature. Right, so as we said, CTAD kind of grew over time. In C++17, we only had support for classes that had constructors, which is really non-aggregates. And then with the paper P1021 made by Mike Spertus, Timo Dumler, and Richard Smith, we also got support for aggregates and for alias types. We also got support for non-type template parameters. Oh, sorry. I skipped a slide. So, when does it work? Whenever I have an initialization of an object of class template, and I don't specify my class template arguments, I get a deduction. I get a deduction in the copy initialization case and in the direct initialization case. I don't even have to have an initializer. In this case, my template argument is deduced from the default template argument for T. I get it in new expressions. I get it in the function style cast expressions. And this is, again, a nice usage for CTAD. I don't have to specify which kind of mutex I want to lock. I just lock it. And also, I apologize for the naming there. That's atrocious. I don't get it in pointers. I don't get it in references. And I don't get it in arrays. Now, when I saw that, I kind of thought, do we actually need this? I thought, well, maybe auto does the same thing. However, auto still doesn't work for arrays. And I think it would be kind of nice if it did. It would be really nice to get template argument deduction in arrays, because if we have it for aggregates and arrays are aggregates, maybe we could one day. I don't know. Something to think about. Unfortunately, as Ville Voutilainen pointed out, and he is somebody I spoke to a lot when I wrote this talk, auto doesn't actually do the same thing. We do still lose a part of information. We lose the information that we want, a type S. However, you can't always use auto. For example, in the cases x1, x2, and x3, if you wrote auto instead of S, we wouldn't get an S, we would get an integer. There needs to be a way to specify that I want a type S. So CTAD does something that auto doesn't. In C++20, we also got support for non-type template arguments. So if I had a template function foo that takes a non-type template argument, I didn't have to specify exactly which specialization of S it takes. I can just let the compiler deduce it. And if you're really careful, you can see that that's now actually a template of templates. So I write one, but I get it for all the specializations of S. Where it still doesn't work, it's in function parameters. I don't know if we'll ever get this. I'm not even sure whether it's being discussed. But if we do get it, then this is going to be a template function. So how does it work? Here I have a class of template that has two constructors, and then I write initialization of an X, and I don't specify the template arguments. So the compiler goes away, and it does something like synthesizing the make functions. So it creates a set of notional template functions. I'm going to call them deducex for this experiment, based on the constructors of the primarily cast template. Now you'll see a star there. The star means that I'm not telling the full truth. I'm giving you a half-truth. But this half-truth is enough for you to understand what's happening. And then once we have this set of notional template functions, I just substitute the initializer inside, and I get whatever is deduced. Again, there's a star, meaning I'm missing something. And we'll get to that. Once I have t deduced, I substitute it back into the statement, and then I proceed with initialization as I normally would. So if we go back to our example, I have my class. It has my primary template class has two constructors. I have one deducex which sort of mimics the constructor, the first constructor. It has template arguments which match the template arguments of the class. It has the arguments that match the arguments of the constructor, and it returns the instantiation that we want to get. And then, once the compiler goes and deduces int, it substitutes its int back into x and invokes the correct constructor, and we're done. These things here, these notional function templates, they're called deduction guides. This is the signature that the standard calls out. The standard doesn't give it a name, but this is the signature that the standard has. However, if we just wrote this in code, it would be impossible to distinguish between this and normal function templates. So we have a special syntax for expressing the deduction guides. So if I was to express these deduction guides in the official syntax, they would look like this. So they still have the template parameters as they had before. See if I can go back. I can. Woo. The name is the name of the class that we're trying to deduce. The arguments are the things that we're trying to match. And then we return the specialization that we want to get if this deduction guide is matched. So these are the two ones that we get from the constructors that we have of the primary template. These implicit deduction guides work with all sorts of things, anything that you can imagine. So they work with default template arguments. They work with concepts. They work with variadic arguments. They work with template constructors. They also work with concepts on your constructors too. Not sure whether I spelled this out correctly. I rewrote my talk yesterday completely because I was not happy with how it flew. So I hope there are no typos. If there are, just let me know and I'll fix it. Not now, but after the lecture. Other than the deduction guides that you get from the constructor of the primary template, there are certain special deduction guides that you get. One of them is a deduction guide that you get if your class has no definition or if it has no constructors, and it imitates a default constructor. This is kind of useful if you have default template arguments and no primary template definition for whatever reason. Maybe your primary template is not meant to be instantiated. And then a slightly more controversial copy deduction guide. Copy deduction guide mimics a constructor that takes an object of same type by value, which means it beats quite a lot of other initialization. And whenever you try to initialize with an object of the same template class, you're going to get the same template class type deduction. Did that make sense? Does anyone have any questions? Okay. If you have any questions, just raise your hand, we can get to them. So going back to the example, I kind of, again, bent the truth a little bit. I didn't tell you the whole truth. So we had the two implicit deduction guides that we got from the constructors of the class, but there was also this copy deduction guide that we just mentioned. And in the case that we looked at, which was an initialization from an integer, it didn't matter because when I initialized from an integer, I will always get number 1 deduction guide. That one will always kick in. However, now that I also have this copy deduction guide, which I always had, you just didn't see it, and I try to initialize a y from an x, that's the one that's going to kick in, and I'm going to get deduction of x in y case to also be an integer. So x and y are going to have the same type. Now, other than the deduction guides that you get from the compiler, you can also write your own. And you might ask yourself, why would you want to write your own deduction guide? Well, the motivational use case was initialization of containers from iterators. So I have a vector here. I've taken out everything that we don't need for this example from a definition of vector. I also removed allocators. I hope John doesn't mind. But all we have to know about this constructor is that it takes 2 iterators. And below, I've written out the deduction guide that we get for this constructor. Now, if you know a little bit about template argument deduction, you will see that there is no way to deduce t from this signature. The t doesn't appear in the arguments. But we can get to t, because t lives inside the iterator traits of our iterators. And in order to get that deduction, we have to give the compiler our own rules for our class to use when it's trying to do template deduction. So let's write that one. We want to get template deduction for our vector. We want to match the 2 iterators. And when we match it, we want to deduce the vector of the iterator trait's value type. And now we can initialize our vector even with iterators. And everything works. Yay. This is not the only case. There are other cases where you want to write your own deduction guides, and if you look into the standard, quite a few types now have their own deduction guides for different reasons. And not only that, your deduction guides don't actually have to be templates. They can be non-templates. Here is an example of why you would want one. So I have a primary template Bob. It has no constructors. And then I have a specialization for integer, and it has an integer constructor. So what I want to do when I initialize it with an integer, I want to get the integer initialization so that constructor gets hit. But I can't do that with implicit deduction guides. So I write something like this. If I find an int, I want to deduce Bob of int, and that's it. This deduction guide is not a template, but it works. So going back to the things that I said, the way it works is you create a set of notional template functions based on the constructors of the primary class. Let's fix that. You create a set of deduction guides for the class based on the implicit deduction guides and whatever deduction guides you write yourself. And then you deduce t from the deduction guides using template argument deduction. There's still a star there. We're still missing something. What we're missing is the difference between CTAD and normal template argument deduction. And there are 2 major differences. The first one is that CTAD doesn't do forwarding references. So let's remind ourselves a little bit what a forwarding reference is. Here I have a function template foo. It takes trefref. And when the compiler goes away to try and deduce the template arguments for this function template, it has a branch that says, if you find a trefref, and t is a template argument of a function template, go down this route. And that route says, if you invoke this function with an L value, deduce an L value reference, and if you invoke it with an R value, it deduce an R value reference, which means that we actually get 2 different instantiations based on whether we invoked it with an L value or an R value. We needed this because when we introduced move semantics, there needed to be a way of writing generic code that forwards the value category down the call stack. And this is how it works. Notice that it also deduces reference types rather than normal types. However, when we talk about class templates, in our constructors, we don't get perfect forwarding. If I have my class X and it has 2 constructors, and I explicitly specialize it with an int, and I try to invoke it with an L value, it will go to the first constructor that takes a const tref, And if I invoke it with an R value, it will go into a trefref constructor. In other words, trefref in this class constructor is just a plain R value reference. There's nothing special about it. So if our CTAD deduction mechanism treated this as a forwarding reference, then we would get deduction guides matching for cases where that particular constructor wouldn't hit. So we just don't do it. And that way we get the right answer for R values and L values. The other difference is that CTAD is very much all or nothing. If you don't specify any template arguments, you get CTAD, but as soon as you specify one, CTAD is disabled, and you have to specify all. And there's quite a lot of noise on Stack Overflow about this. People want partial deduction. And we actually had a paper that proposed partial deduction. But the author withdrew it because there were good reasons why we couldn't make this work. And these are the reasons. Consider this class. It has one default template argument. And the code that you see here, this declaration, it's perfectly valid. The first one, T, is deduced. The first one, T, sorry, is explicitly specified. And the second one is defaulted. Now, if we enabled CTAD in this case, then you might get deduction from 2, and instead of getting char, you would get int, and the meaning of code would change. And that's not the only reason. There's another reason. If you have variadic arguments, and we have an initialization like this, have we specified all the template arguments, or have we specified one and want the other ones to be deduced? This is not an answer this is not a question that we can answer, so we haven't. So, now that we know what CTAD is, how it works, what roughly it does, what should you be aware of? We spoke about the copy deduction guide earlier, and that is something that sometimes confuses people. So let's take a look at an example. I have a vector of int a here. This is definitely a vector of int. And then I initialize b with an a. Now, who expects b to have the same type as a? Can I have a show of hands? This is not a trick question. This is just, what do you intuitively feel should happen? Thank you. Let's take a different example. This time I have a make function. And what my make function does is it takes everything you give it and put it into a vector. Now I invoke it with an int, and I get a vector of int. I invoke it with a vector of int. Should I get a vector of int? Who thinks that? Is there anyone? Thank you. This is a completely valid answer. You should expect a vector of ints if you have a function that puts whatever you give it into a vector. And this is what the discussion came down to. When you write something like this, do you mean to have a container of ints, or do you mean to have a container of ints? One thing that I learned since I started going to the committee meetings is that the answer to the question of what is the right thing to do is not always obvious. People disagree. Depending on the environment they come from, the problems they want to solve, their experiences, they expect different things and they want different things. But the consensus was that it's more common for people to expect this to be resulting in exactly the same type for B2 as it is for B, which is why we have the copy deduction guide. And it doesn't mean that you can't write generic code. It just means that you shouldn't use CTAD in generic code. So in order for me to make this a function that puts in a vector anything I give it, all I have to do is explicitly specify my template arguments. Problem solved. Now, it does mean that people who write generic code can't always get to use CTAD, but more of us don't write generic code than people that do. And I said that wrong because I can't write generic code, but never mind. Um, Here's another example. I have a pair of an integer and a char, and I initialize tuple with that pair. And the question is, what do I get? Don't guess. Let's open the documentation. This is from C++ reference, CPP reference, which is pretty much the same thing as looking into the standard most of the time, and sometimes it's easier to understand. So here are the constructors that take a pair. They do something special compared to other constructors, otherwise they wouldn't exist. So I scroll down to look at the specification of them, and it says, construct a two-element tuple with each element constructed from the corresponding element of P. And then I scroll even further down, and look, I have deduction guides. And there's a deduction guide for a pair. So if I give it a pair, I'm going to get a tuple. Going back to my code, what is the deduce type here? Anyone? Exactly. Read the documentation. RTFM. This is not CTAD core functionality. This is library design. This is how the author of tuple wanted tuple to behave. So, just something to think about. The other argument against CTAD is that it's something that you get without knowing that you get it. So, this is a structure Bob that was written before C++17 when there was no CTAD. They didn't know CTAD was going to happen. They didn't care about it. And then a C++17 user wrote this initialization of Bob, got CTAD, and they were happy. But then the author of Bob made some changes, and the changes that they made disabled template argument deduction. And all of a sudden, users' code broke, and they're not happy. This is a valid argument. I mean, if this happens, you're just going to have to renegotiate with your users. But whether that's a reason to hate on CTAD, I'm not really sure. But that's definitely a possibility. And in fact, that's one of the ways you can, one of the tricks that you can do to disable CTAD if for some reason you want to disable CTAD in your class templates. That means that all of the implicit deduction guides will no longer work apart from the copy deduction guide, which will still kick in. There's no way of disabling that, I'm afraid. Right. I think this is all I had to say about how CTAD works. The question of whether you want to use it or not use it is down to you. But I do think being familiar with it and knowing how it works makes for better decision making. So some advice that I can give you, if you're a user of class templates and it comes to what the question is of specifying template arguments, be careful in the same situations as you would with function template argument deduction, things like quoted strings. Also be careful when writing generic code. If you don't know how your type's going to behave when it receives different types, then be as explicit as you possibly can be. Be careful when you write things where a container is taking a container, simply because those containers might behave in a way where it doesn't do what you expect it to do. Be careful when you're initializing with an element of the same template class. And in general, just read the documentation of the things that you're doing so you know that what you're doing is right. And if you're a vendor and you're writing template classes, you're going to have to get familiar with CTAD because you're going to have to test for it. You're going to have to test that your implicit deduction guides do what you want them to do. And if they don't, you're going to have to write your own. And more importantly, you're going to have to document it so your users know what they're getting. And if you don't really want to support CTAD, then consider when you want to disable it using that trick that we saw earlier on. And on that note, any questions? Hello. Hi, Matthias.
Thanks for that good explanation. On the question of those partial CTAD, do you know whether there was a discussion about disambiguation, like putting a comma auto?
I don't know. I know that Timo was the author that presented that, and I know that he withdrew the proposal because he simply didn't think it was worth pursuing. But I think when you think about that, you have to also think about the overhead that the additional syntax brings to the complexity of the language and the compiler versus the benefits that you get.
On the other hand, it would solve the auto comma int case where I want to fix the second parameter.
Possibly, yes.
Okay, so
it's something to think about.
Ask Timo whether it was considered.
At the moment, there isn't a good way out. If somebody comes out with a good way of distinguishing what the user wanted to say without breaking past code, then we might get it. But like I said, CTAD is a convenience feature.
Right.
It isn't something that I think people will want to invest a lot of effort in to make certain corner cases work well, although you never know.
Well, it's a bit more than a convenience feature for me in terms of replacing auto with something more specific, but still getting deduction, right?
Yes.
So,
and like I said, even when you start learning new things like ranges, like if you also had to think about the class template argument deduction, like it does help a lot. So yeah, if you have a paper to write.
I have too many already. The other question is on alias templates.
Yes.
Can you write deduction guides for these? I think you cannot.
No, you can't, because the aliases are supposed to behave the same way as the original class template.
Right, but
now, we haven't covered the rules for the alias templates here, and we also haven't covered the rules for the aggregates. They're kind of special, but no, you can't customize
because
it
they
aliases.
can have non-deducible arguments, right? And so
they could, yes, but you always fall back to the primary template class because your aliases are supposed to behave in the same way. If you had a deduction guide for your aliases that don't work with your primary template, then that's not very good.
Thanks.
Hi, thank you for the talk. On the slide with the user-specified iterators, sorry, not iterators, deduction guides.
Why is this dead?
I think you went to sleep.
I went to sleep. I'm sorry, I'll wake up. More caffeine. Which slide?
The one with the user-specified deduction guides that you had.
I had one with vector.
Yeah, is T supposed to be input iterator instead? The second one, I think.
Sorry?
I think it was the next slide. Sorry.
Yes, I thought that too.
Did I have something wrong?
I think the T and the first T should be input iterator.
Yeah.
The first T should be input iterator.
Template type name input iterator.
No, type name T, because you don't deduce input iterator.
But you're not providing a T, you're providing input iterator.
Yes, sorry, yes, I apologize. Yes, input iterator, I apologize. Yes, it should be an input iterator, I apologize. Yeah, don't look at that, I'll fix that. Thank you.
Question about the forwarding reference issue.
Okay.
So you say it will deduce a forwarding reference as just an R value. So the example you showed had both an L value or constant L value and an R value constructor.
Yes.
There. If you took out the first constructor,
yes.
Would the first deduction fail because there's no matching constructor?
Well, if you took out, you wouldn't have the first one. That's the whole point. So if you took out the first constructor, you would only have the second deduction guide, this one here.
Yes.
And that one wouldn't kick in for L values because that's not a forwarding reference.
So
that can only match R values.
So you would need to create an explicit deduction guide.
Yes.
Because the original constructor does accept an L value.
Which one? TRefRef.
If you left out, yeah.
No, it doesn't. TRefRef doesn't accept L values because that's an R value. That's the whole point in classes.
Oh, right, because it's not a template. It's not a template constructor.
Yes.
Right. Okay. Thanks.
Welcome.
Oh, Hi. So
Hello.
Thanks for the talk. I have a little bit of a controversial question. So I noticed that the syntax for deduction guides is very similar to syntax for function definitions. Now I understand why.
Yes.
But then it's too similar. When you cursorily examine the code, it's like, oh, is it the function or is it the deduction guide? So what was the underlying reason not to choose more expressive syntax, maybe with the word guide in it or something, as opposed to making it too close to the function syntax?
Syntax of new features is always difficult, and it really comes down to what is proposed and what's the best option of the things that's proposed. That's really what it comes down to. So if someone thought that this is sufficient enough, it kind of looks a little bit like constructor definition, except it isn't a constructor, right? It has this, it doesn't have a return type.
Yeah, if you add an auto keyword after the template, it becomes a function definition.
Yes, but you can't have that. But yeah, it is. I agree. It's not really. That's just the syntax that we had. It was considered good enough.
I see. Thank you. And I have a follow-up on the. Okay, we have this slide. Good. So actually, while you were talking, can you put it back? Thank you.
More caffeine.
Or does it the signal? Is it the signal to me to shut up? No, I'm talking about the forward references. So we had the perfect slide. Oh, okay. Thank you. Yeah, that one. So I actually did an experiment. I removed the brackets int or angles int, and it still works.
Yeah, it still works. The reason this was just to demonstrate that if you have an explicit specialization, this is how it would behave. So if you have an explicit specialization and you invoke it with an R value, you hit the second constructor. And if you invoke it with an L value, you get the first constructor. And you kind of want to get the same behavior in your deduction guides. You don't want your deduction guide deducing something that will hit another constructor.
Oh, I see. Thank you.
Welcome.
Hi. Thanks for the talk. So I have a comment and then a question. Well, really kind of a nitpick, I should say. The comment is that I think I find one of the most useful versions of CTAD to use in code is that with non-type template parameters, because you can just put a class template like ... right? And those all deduce to the same class template specialization, but with like different, specialized with different arguments. And that's like such a powerful thing to express in a template. So that's another use case that could be worth investigating for people. And then the nitpick, which is that why? So we're already reusing the most complicated syntax for specifying deduction guides, which is essentially a constructor.
Yeah.
Why did we limit it to you have to put that thing in the same scope as the class definition? So it makes it super awkward to have like nested classes, and then you put the deduction guides in the enclosing class scope as opposed to like at namespace scope.
I don't know. That specific question, I don't know. I understand how this is difficult, but yes, I guess the idea is that you want to keep a deduction guide close to your function definition so you don't have to go away and look for it. I don't know. I don't know whether that satisfies you, but that's the best I can give you.
Thank you.
Welcome. Hello.
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 Any design thoughts on using tags and constructors to guide CTADs to specifics, like specializations? Like if I have a tag type in a constructor, I can just use that to just use CTAD instead of specifying any template parameters to go to whatever specialization I need.
You can use, you mean you having deduction guides that are not template and just
right,
use
it's based on a tag inside a constructor, so it can go to the specific specialization. Is that good design, bad design, or you haven't played with it enough to?
I'm not a library designer. I sit in core, like give me all the weird classes.
You come visit once in a while.
Every now and again. I'm a tourist for now. Hello.
Hey.
Hi.
So for disambiguating container T from container T, what comes to mind for me, and I haven't thought this through at all, is using curly braces versus parens. So that if you use curly braces, you would get container T because it's an initializer list versus.
That's actually something that has been discussed. I spoke to a few people when I was writing this class, mostly people that don't like CTAD because they wanted to understand why they don't like it. And it was David, I believe, who said he wanted that. He wanted to have a differentiation with curly braces versus parents, but people just said, no, this is what we want. If you're writing generic code, then don't use this. Sorry.
Okay, sounds good.
Any more questions? I do want to say a thank you to Ville, who hopefully is watching this talk. At one point, he spent numerous hours debating with me the good sides and the bad sides of CTAD, so I want to call him out specifically. And I want to thank you all for coming to my talk.